Back. So the subject of today's lecture is simple. We're going to do one thing, and that is we're going to prove that CDFT, which we've been talking about, is injective. Okay. Why do we care? Okay. Well, when we talked about transforms very generally way back in lecture 1, and when I talked about Fourier transforms a little bit heuristically at the beginning of our discussion of Fourier transforms, what I implied was that you would like to know if you take a function here and you calculate its transform here, are you able to uniquely recover the signal from its transform? Okay, and that question is precisely the injectivity of the transform. Okay, so this is an important thing. Obviously, just the way I phrase this property tells you that it's important, which is, can you recover an f from CDFT of f? Okay, and if you can't, then it really limits the usefulness of the transform if you can't recover the thing you're transforming from the transform. Okay, so we're going to have more to say about these kinds of things in the subject of invertibility of the CDFT, which we'll talk about a little bit more carefully next time. But today, what we're doing is we're essentially asking about injectivity of the transform. We're asking, does there exist a left inverse? Okay, so is there a mapping which goes from here into here? And you might want to call that the inverse from little c0 into L1 per, with the property that if you apply this inverse to the CDFT, it's the identity. Okay, so that's the idea that we're after here. Okay. All right, but today's lecture is meant to just be establishing the technical fact that the CDFT is injective. So this is an interesting proof. So I want to just devote one lecture to it. It's an interesting and important proof. Okay, so in the proof, so to establish the proof, we're first going to prove that the CDFT is injective restricted to continuous functions. Okay, so first we're going to prove So notice that CDFT is linear, okay? And so to establish that a linear map is injective, it suffices to show that its kernel is equal to 0. Okay, so if you take the transform of something, it's equal to 0 here. Injectivity is equivalent to saying that the resulting signal must have been 0 here. Okay, so first we will show that we have injectivity on continuous signals. Okay, so in other words, we're going to show that if f is in C0 per, and if its CDFT is 0, then f 0. Okay. All right, so the CDFT of f equals 0 implies, just by definition, that the integral from 0 to t of f of t, e to the minus 2 pi t over t is equal to 0 for every n. Okay. And so this implies that the integral from 0 to t, 0 to t, f of t, g of t, t is equal to 0 for any g that is a finite linear combination of harmonics. Okay. So the assumption is that, of course, it's 0 for every individual harmonic, and just by linearity of the integral, if g is a finite linear combination of these guys, then the integral will also be 0. Okay, so what I will do is consider a rather specific finite linear combination of harmonics. Okay. All right. And I'll just state this as a fact. Oops. So we're going to look at a signal that we've seen before, namely the periodic Dirichlet kernel, but I'm going to tell you something about the periodic Dirichlet kernel that we've kind of seen, but haven't quite phrased it in this way, and that is the following thing. That the periodic Dirichlet kernel, which we denoted like so, is equal to, right, so what you do, so it's an interesting formula, is first you sum all of the harmonics up to some k. Like so. Okay, so these are the harmonics from n going from minus k to k. All right. Then you average those over k from 0 to n. So you take the average of the first capital N of these. All right. So you sum n equals, k equals 0 to n minus 1, okay? And then you average, so you divide by n, okay? All right, so we had this formula for the periodic Dirichlet kernel that we wrote down before, okay? And that formula is that it is 1 over n sine squared pi n t over t over sine squared pi t over t. Okay, so that was the definition of this Fourier kernel. So sorry, I kind of stumbled and stammered in such a way that I had to erase myself. Okay, so the point is that we have, by this formula, an expression of this thing we've seen before, which is the periodic Fourier kernel, as a sum, a finite sum, a particular finite sum, but nonetheless a finite sum of these harmonic functions. Okay, and so by my observation here, we must have, therefore, that the integral from minus t over 2 to t over 2 f of t Fourier kernel of t dt is equal to 0 for every n. Okay, so I've done a couple things here. I replaced some random finite linear combination of harmonics with a specific finite linear combination of harmonics, the periodic Fourier kernel, and I've also shifted my integral from being defined on 0 to t to minus t over 2 to t over 2, which totally doesn't matter. You just integrate over a period that is convenient for you. Okay. All right, so the CDFT of f being 0 implies this, okay, for every n. Okay, so now suppose that f is continuous, right? I'm working in the continuous case for the time being. Is not 0. Oops. Is not 0. Okay. But that its CDFT is still equals 0. Okay, so again, the CDFT being 0 implies that, but I'm going to now impose the condition that f is not itself 0. Okay, so what this means, if f is non-zero, it means that there's some time at which f of t is non-zero. Okay, so without loss of generality, I can assume that that time is at t equals 0. Okay, and the reason I can assume that without loss of generality is if f is non-zero at some non-zero time, then by shifting f, I can ensure that the shifted version of f is 0 at 0. And if you remember the formula for the CDFT of a shifted signal, the CDFT of a shifted signal is 0 if and only if the CDFT of the original signal is 0. Okay, so when you shift the point at which f is 0 to happen at t equals 0, you don't change that fact. Okay. All right. So, in summary, we can assume that f of 0 is not equal to 0. Okay. And then, without loss of generality, assume that f of 0 is greater than 0, just so I can draw some pictures more easily. And of course, that's true just by changing sign. And if that's true for f, it's also true for minus f. Okay, good. And so now let alpha be some positive number. Be such that, okay, f of t, so I know that it's 0, f of t is equal to 0, okay, and I also know that f is continuous. That's part of my assumption that I have ongoing right at the moment. And so if I take an interval around 0 with alpha, I can ensure that on that interval, f of t is greater than or equal to 1/2 f of 0. So that's going to be true for t there. Okay, so in pictures. Okay, so let's say here's f, and f is non-zero at 0. Okay, so it looks like whatever it looks like, but I know for sure that because it's 0 at 0, it's going to be, so it's positive at 0. It's going to be positive in some neighborhood of 0. So, it might look something like that. Okay, and so this value, therefore, is f of 0, and that value will be 1/2 f of 0. And so I can ensure by choosing alpha small enough, okay, that on that interval from minus alpha to alpha, f is greater than a half f of 0. Okay, so that's the idea there by continuity. All right, good. Okay, so so now what I'm going to do is I'm going to look carefully now at the condition that okay, so we have that 0 is equal to the integral from minus t over 2 to t over 2 f of t Fourier kernel okay, and what I will do is I'm going to break this integral from minus t over 2 to t over 2. I'm going to break it into 2 bits, one being from minus alpha to alpha. All right, so f of t, f of t, and t, dt, and then over the rest. So this is from minus t over 2 to t over 2. Take away minus alpha. All right, so it's f of t per t and t dt. Okay. All right. So now what I'm going to do is I'm going to use the fact that f of the periodic Dirichlet kernel is an approximate identity. Okay. All right. So the periodic Dirichlet kernel sorry, I'm saying Dirichlet, I mean Fourier, sorry. Because it's not true, of course, of the periodic Dirichlet kernel. Okay, so that means a couple of things. Okay, so the first thing it means is that the integral from minus t over 2 to t over 2, and so I have to be careful how I say that, right? So these are when I say the periodic Dirichlet kernel is an approximate identity. What I mean is the sequence indexed by little n. Okay. All right. And so one of the conditions for that is this. Okay, and then another condition that we're going to use is that the limit as n goes to infinity of the integral from, it's going to be this bit here. Okay, minus t over 2 to t over 2, take away minus alpha alpha f t t dt is equal to 0. Okay, so the total integral for every n is 1, and the contribution of the integral away from any little neighborhood around 0, the contribution of of f away from that little interval around 0 goes to 0 as n goes to infinity. Okay, and this was the behavior that I sketched when we introduced the Fourier kernel. So minus t over 2 to t over 2, that for small n, it kind of looks like this. Okay, and then as n gets large, gets tall, right? Because its value at 0 is n. Okay, so it gets tall and it's kind of rapidly oscillatory, or more rapidly oscillatory. Okay, and so the contribution of this integral, which is 1, okay, becomes concentrated solely around some interval around 0, okay, and the rest of it goes to 0, okay. All right, so now what I'm going to do is I'm going to use those two facts together to arrive at a contradiction. Okay. All right. So first I am going to look at this bit here. Okay. All right. So the integral from minus alpha to alpha f of t, f per t n of t dt. Okay. Well, first thing is this is going to be greater than or equal to, because on minus alpha to alpha, f is greater than 1/2 f of 0. Okay, so it's greater than or equal to, and notice also it's important here that the Fezia kernel is positive. Okay, so that's another property of the Fezia kernel I'm using. Okay, so I get 1/2 f of 0 integral from minus alpha to alpha f per t n t dt. Okay. Now, what do I know? I know that for I know that the integral over all of a period is equal to 1, and I know that the integral outside this region goes to 0 as capital N goes to 0. Okay, sorry, capital N goes to infinity. And so I know that by making n large enough, this thing will be larger than, let's say, 1/2. Okay, because I know that as n goes to infinity, this has to go to 1 because this is equal to 1 and this goes to 0. Okay, and so I can say that this is greater than or equal to 1/4 f of 0 for n large enough. Okay, so there's some large enough n's, capital N, so that for any n beyond that, I'm going to get an estimate like that. Okay. Okay, now what about this bit? Okay, so what do I know about f? So I know f is continuous. I don't know much about f other than it's continuous, but that's going to be enough because it's going to be bounded. Okay, and then the contribution from the integral of this bit is going to go to 0. Okay, so let's work that out. Okay, so the integral from over the rest of the domain or the rest of a period. Okay. And so let's estimate the size of that, right? So f of t, f per t, t dt, right? And what I want to show is that that becomes as small as I would like, okay? And then that'll guarantee, if this is small in magnitude, that when as n goes to infinity, and this is bounded below in magnitude for large n by 1/4 f of 0, which is positive, okay, then as n goes to infinity, the point is that the limit of this as n goes to infinity should be positive. Okay, so let's just sort of work through the details of that. Okay, so this is the integral, again, over this bit. All right. And so, I'm going to move the absolute values inside the integral. Then I'm going to notice that f is continuous. And so its infinity norm is bounded on any period. Okay. So I get f infinity, f per t, t, t. Okay, because again, f is positive. Okay, now I know, so I can of course take the this is a constant, so I can take that outside, and so I'm left now with this thing, right? And as n gets large, that goes to 0. Okay. And so by making n large enough, this can be chosen to be less than or equal to 1/8 f(0), okay, for n large enough. Okay. And so the point is, if this term is bounded below by a quarter f of 0, okay, and then the other term, this term is bounded in magnitude. It may be positive or negative, but it's bounded in magnitude by an 1/8 f of 0. Then I obtain that integral from t over 2 to t over 2 f of t f t t. It must be greater than or equal to 1/8 f of 0 for n large enough. Okay. And this is a contradiction because my assumption is that this is equal to 0 for all n. Okay. Okay, so then we can conclude that the CDFT restricted to continuous functions is injective. Okay. Now, what you want to do is use that to arrive at the proof in the general case. Okay. All right, so now I'm going to let f be in L1 per t, and I'm going to assume that its CDFT is 0. And I want to show that f is 0 in L1 per. What that means, of course, is because L1 per consists not of signals, but of equivalence classes of signals. What I want to show is that this implies that f must be 0 almost everywhere. Okay. All right, so here's how I'm going to do that. I'm going to define capital F of t to be the indefinite integral. Okay, so this implies, for example, that f is f here, sorry, this is only going to be defined for t's between 0 and t. Okay, so and then what we're going to do is we're going to take f and we're going to periodically extend it. Okay, but first we need to understand some things about f, capital F. Okay, so note that f is, okay, so still thinking of f as just being defined on 0 to t. So f is absolutely continuous. remember that just means that it's the indefinite integral of an integrable function, right? Namely f. Okay, and it's absolutely continuous. In particular, it's continuous. Okay, and moreover, okay, f of t, not that t, that t, by definition is the integral from 0 to t, f of t, t, okay, and this of course is just the CDFT of f at 0 by definition, okay, but I'm assuming that CDFT of f is 0, so this is equal to 0, and that's also equal to f at 0. Okay, and so the point is that f is continuous, absolutely continuous, but continuous on 0 to t, and its value at t and 0 match up, and so this means that f is in C0 per. Okay. All right, now let's figure out what the CDFT of capital F is. Okay, but we know the CDFT of capital F well, we know it for most n's by our previous result about the relationship between the CDFT of a signal, which is absolutely continuous or differentiable, and the CDFT of its derivative. Okay, so by our relationship between the CDFT of F and the CDFT of F prime. Okay. Okay, so this now plays the role of F prime, right? Okay. We have that the CDFT of F at n over t is equal to, right, so keeping in mind that you know, f is the thing that's being differentiated in that previous theorem that we had, and so the point is you divide by 2 pi I n over t, which or multiply by 1 over that, so you get this. Okay, FCD of f prime. Okay, but what's f prime? Well, f prime is just little f, of course. Okay, and so this is equal to 0 by assumption. We're assuming that the CDFT of little f is equal to 0. And this is valid as long as n is not 0. Okay, now when n is equal to 0, it may not be the case that the CDFT of capital F at 0 will be equal to 0, but we can fix that because remember that the CDFT of any signal at the 0 frequency is just the integral of the signal from 0 to t, and so we can basically subtract that off is the point. Okay. Okay. So if I now sort of redefine f to be g, okay, and like I said, I'm going to subtract off its average. Okay, so minus 1 over t integral from 0 to t f of t. Oh, sorry, I don't want t there. S. Yes. Okay. All right. Then so in other words, G differs from F just by a constant. Okay, and so it follows immediately that the CDFT of G will equal the CDFT of F at a non-zero ends, and then it will be also 0 at 0 ends because this ensures that G has 0 average over the interval. Okay, and so then FCD of F of G at any n over t is equal to 0. Okay, again, for two reasons. One being that for non-zero ends, the CDFT of the constant function will be 0. And then the CDFT of G will be the same as the CDFT of F, which I've shown is 0. Okay, and then for n equals 0, just a direct calculation, but also just using the fact that I've subtracted away from F its average, that ensures that I get 0. Okay. All right. So, all right, so I know that this is true, okay, but I also know that G is continuous, okay, and I know that G is continuous because F is continuous, and G differs by F just by a constant. Okay. So since G is continuous, the first part of the proof where we showed that the CDFT is injective on continuous signals gives that that G is equal to 0. Okay, so it's 0 everywhere, right? A continuous it's a continuous function and it's identically equal to 0. But not only is it continuous, but it's absolutely continuous. Okay, so now the fundamental theorem of calculus okay, so what I mean the Lebesgue integral version of that. Okay, so you'll see what I mean by that. Okay, says that 0 is equal to G prime of t, okay, and that's true just because G is equal to 0, right? So 0 is obviously the derivative of the 0 function is 0, okay. Now G is equal to F plus a constant, and so this is equal to F prime of t. Okay, and this is now where we're going to use the fundamental theorem of calculus, because this is d by dt, integral from 0 to t, f of tau, d tau. Okay, and now the freshman version of the fundamental theorem of calculus would tell us, because that applies in the case where f is continuous, but it's not continuous now, it's only in L1, but still it holds almost everywhere. Okay, for almost every t. Okay. All right, and that's all I needed to show. Okay, so that shows that the CDFT is injective. Okay. All right, so so what does this mean? So this means that given f in L1 per t, okay, there exists a means of recovering f from its CDFT. Okay, that's precisely what injectivity means. Okay, and then the question is, what is this means? Okay, and that is what we will talk about next time. And so this is really the proper discussion of the inverse of the CDFT.